In a previous video, we looked at the Tromino problem for tiling an 8x8 board, and in that we solved an induction problem that solved our problem for all powers of 2. So if you haven't looked at that video, take a look back, watch that one first, and then return to this one. Because now we're going to move on to some special cases. Our problem at hand is to try to look at which squares, when deficient, can be tiled with Trominoes. In this next problem, we're going to look at the 10x10 board, and we're just going to start by playing around with it. So if you have a 10x10 grid, the idea is if you remove any one square, let's say we remove this square right here, could you tile the rest of it with the Tromino shape? So if you've never tried this problem, give it a try. This is the problem we're going to build up to solving today, and again, in a systematic way. Okay, so our story is going to start with 5x5 boards. The 5x5 boards have some cases where you can solve the problem and some cases where you can't solve the problem. In particular, the ones below, whenever the deficiency is in a corner, the center of a side, or in the very center of your grid, it is possible to solve these tiling problems with Trominoes. So give this a try, see if you can fill up the rest of the spaces here with Trominoes. Pause the video now, we'll give you the solution in a moment. Okay, so those scenarios are possible. If we scroll down to the example below, it turns out that the other scenarios, so when our deficiency is not in a corner, side, or very center, if it's in one of the white squares below, we cannot solve the tiling problem. So in this part, we're going to try to prove that we cannot solve the tiling problem when the deficiency is, let's say, for example, right there. Why couldn't you solve the problem? Let's try to think about it for a moment. Again, pause the video. We'll give you the solution in a moment. Okay, so a reason why we cannot solve this tiling problem in front of us, if, for example, that square was missing. Why can't we fit in Trominoes into our space? Well, let's remind ourselves above, we did successfully solve some of these Tromino problems. For example, in this grid right here, how many Trominoes did it take to solve the problem? Well, 1, 2, 3, 4, 5, 6, 7, 8 Trominoes fit into that grid. So the space that we need is 8, and that makes sense. 8 times 3 is 24, plus that one missing square makes 25. So back to our problem below, we know that 8 Trominoes are needed to fill in the rest of the space. But looking carefully, there are 9 black squares in front of us. And each black square, so if we look at this black square right here, when we place a Tromino to cover that black square somehow, maybe like this, or maybe like that, or possibly even like that, no matter how we place that Tromino to cover that black square, it won't cover any other black squares. So one Tromino is required to cover that top right black square, and the same goes for every other black square in our picture. So this shows that we cannot finish this tiling problem because 9 Trominoes are required to cover the black squares, but only 8 Trominoes fit in this entire grid. So therefore, in all of these cases, when one of the white squares is missing, we cannot finish off the tiling problem. So next on our chopping block is the 7x7 boards. We're going to try to explain why all deficient 7x7 boards can be tiled. So key in what I just said is all deficient. So we need to make sure that the deficiency could go anywhere. And we're going to use symmetry to help us out here. So the first notion of symmetry is we're going to rotate so that our deficiency is in the top left. So the top left part of the grid will be this section here. Now, in addition, we're going to use a 2x2 sub-block. So my 2x2 sub-block is this one right here. And we're going to kind of eliminate 4 cases all at once, because let's say in this first grid over here, we were able to complete the tiling. So we've got Trominoes there, fill in the space all nice and beautifully. Then you could rotate this 2x2 sub-block so that the deficiency was right there, or the deficiency was right there, or the deficiency was right there. We could always tile that 2x2 block by shoving in one more Tromino wherever the deficiency might be. So with those symmetries in mind, we're going to try to show that P sub 7 is true, and there's really 3 cases to look at. So my 3 cases, fit them on the screen right now, are shown. If we can somehow tile in the rest of the space on these 3 boards, it would actually show that all 7x7 grids can be tiled when they're deficient. So once again, give this a try and see if you can finish off the tiling. I'll put the solution on the screen in just a moment. So if you need a hint, if you got stuck on maybe the first 2, here's a starting point. We've already solved the problem for 5x5 grids. What you could do is section off a 5x5 grid right here and another 5x5 grid right there. And you could make each of these 5x5 grids deficient by placing one Tromino so that it sucks out one of the squares from the 5x5 grids. And if we did that, we wouldn't really have to solve the 5x5 sections because we've already done that previously in this video. So to save ourselves a bit of time, how about we use the 5x5 grid and maybe place a Tromino, let's say right there and right there. See if you can tile now these subsections right there, right there, right there, and right there. Give you a moment to pause and see if you can complete it yourself. Okay, so there's one approach to the first 2 grids that are on the screen. In the third grid, unfortunately, there's no place to squeeze in the 5x5 grid, so we'll just have to try to put Trominoes in to fill up that grid. So I'll give you a moment to try that as well. Okay, so there's one possible solution. Now we can move on to the 10x10 grids. So before we solve our 10x10 grid, we're going to look at a proposition. So this proposition says that if you have a rectangle that is a multiple of 3, so 0 in mod 3, and the other dimension is a multiple of 2, so 0 in mod 2, that rectangle can be tiled with Trominoes. Notice that we're not talking about a deficiency here. There's no deficiency in this sentence. It just says a grid that's a multiple of 2 by a multiple of 3 can be tiled with Trominoes. So the idea is that you can continually build the 2x3 rectangle with 2x3 blocks. So if you have this block that's 2x3 in size, you can build it by sticking 2 Trominoes together just like that. And continually using those over and over and over, you can build up that rectangle. Okay, so now we're ready to move along to the deficient 10 by 10 boards. So to deal with this problem, we've taken a 10 by 10 board and divided it up into the following subsections. So let's take a peek at each of these 4 subsections below: A, B, C, and D. So D is a 7 by 7 subsection, and notice that the deficiency is sitting inside of section D. And we can always assume that the deficiency is there in section D because section D is the biggest, so we could rotate the board so that the deficiency is in the bottom right and place section D there afterwards. Section A is also deficient in a sense. If you consider a 4 by 4 grid, it's actually missing one corner because section D is stealing that corner away from section A. So it's a 4 by 4 deficient section if you think of the corner missing. Sections B and C are quite similar to each other. They are 6 by 3 sections each. So our job here is to explain why each of these subsections can be tiled. Let's start with section A. So section A is 4 by 4. And let's remember earlier along in the previous video, we discussed why all deficient boards, which are of a power of 2, can be tiled. And 4 is indeed a power of 2. 2 to the power 2 is 4, and it's a deficient board, so it can be tiled. Okay, so let's move on to sections B and section C. So these sections have a dimension of 3 by 6. They are not deficient, right? There's no missing square in B and no missing square in C. But if we remember closely, 6 is a multiple of 2, and 3, of course, is a multiple of 3. 2 times 3 is 6, 3 times 1 is 3. So those sections can be tiled by the proposition that we just looked at. So let's write down the details so we have that in place as well. So the only thing that's left for us to do is section D. And previously in this video, we've shown that every single 7 by 7 deficient grid can be tiled. So just referring back to what we did earlier, section D can also be tiled. Therefore, we've looked at each individual section, A, B, C, and D, and we can perfectly fill each of those sections up with our right Trominoes, so the whole 10 by 10 board can be tiled. And it doesn't matter where the deficiency is, because by symmetry we can always stick it in D, and it doesn't matter where it appears in section D. So let's now try to put this theory into action. Let's return back to the very first problem that we looked in this video and try to tile the 10 by 10 board. Okay, so following the directions of what we've done, the first thing that we want to do is section off the grid. So I want to take my 7 by 7 section right there, steal one corner from the top 4 by 4 section. And now each of the subsections are in place. So let's start with the 4 by 4 grid in the top left, section A. What we want to do is place one Tromino in the center, and then all other Trominoes will view as a 2 by 2 grid. In sections B and C, we're going to continually put 2 by 3 blocks in over and over and over until our rectangle is filled up. The last thing that we have to do is fill in my 7 by 7 grid. So we just have to identify which of the 3 cases we are in. And in order to decide that, let's first rotate our grid so that our deficiency is in the top left portion of the 7 by 7 grid. Okay, now we can see that the 2 by 2 subsection that we need to put in is right there. So the Tromino that fills in place will go right there. And now we just need to copy the rest of the solution from earlier along in the video. And now our tiling problem is complete. Thanks so much for listening to this video. We'll see you in the next video where we're going to complete our inductive step to show which squares can be tiled when deficient.